Thank you very much. Thank you very much. Thank you to the organizer for giving me the opportunity to present some recent work of mine, which is about putting together two recent developments in scattering amplitudes. One is surfaceology, which is a novel formalism to compute scattering amplitude without necessarily breaking them up into Feynman diagrams, but instead representing them as a single global integral that computes the entire amplitude. The second one is tropical sampling, is a technique introduced recently by Michael Borinsky. Is a numerical technique to evaluate integrals by a Monte Carlo strategy that is made much more efficient using certain ideas from tropical geometry. So putting together these two ideas, what we get is a numerical strategy to evaluate scattering amplitudes, entire scattering amplitudes, not just individual diagrams, at very high loop orders, let's say at 10 loop orders. Now, if it sounds a little bit too good to be true, it's because perhaps you're wondering exactly which amplitudes I'm talking about. And indeed, for today, I will focus on a very restricted setting. I will be focusing on a massive trace phi cube theory in D equal to space-time dimensions. Why do that? Because these amplitudes happen to be finite, so they are immediately amenable for a numerical integration. In order to go beyond this evident limitation, we will have to understand how to deal with divergences and how to deal with numerators. Now, I am optimistic that this can be done, and towards the end of my talk, I will present a few concrete steps to make progress in that direction. Okay, so this is the plan for the talk. I will begin by giving a very telegraphic introduction to this novel formalism, surfaceology. And then I will present the main novelty, which is this numerical algorithm to evaluate the integrals that we get from surfaceology. And finally, I will present these concrete steps to extend the result. So let's get started. Let me spend a few minutes to explain what is the theory that we're talking about. As I said, this is trace of phi cube. So it means that the fields are matrix valued. They have two indices. And the interaction Lagrangian is trace of phi cube. So because there is a trace, the vertices have a cyclic structure, and a convenient way to represent that structure is to represent them not as cubic vertices, but as a flattened version of cubic vertices. So using a 't double line notation. When you glue together such vertices, you produce a surface. The best way to see the surface is to take the resulting fat graph and sort of stretching it so that it doesn't look like a graph anymore. In this theory, it's very convenient to perform a color ordering decomposition. So to separate the color degrees of freedom from the kinematical ones. What you get, well, this is just the famous topological expansion. What you get is that an endpoint amplitude can be represented as a sum over different types of surfaces. Each surface contributes with a color factor, where we absorb the color group factors, as well as the coupling constant, and so on. The coefficient of that is a kinematical dependent factor, the color order amplitude, and this is the quantity that we will be focusing on today. The amplitude is computed summing over all the graphs, over all the fat graphs that corresponds to that particular surface, so that you can stretch to that particular surface. And they contribute with the usual value of a Feynman diagram. This is a phi cube theory, so this will be exactly the same parametric integrals that we just saw in the talk by Steven. Okay, so the basic insight of surfaceology is to shift the attention from Feynman integrals to curves on surfaces. So curves become the elementary building block of the entire amplitude. And this is based on a simple duality. So if you draw a diagram on a surface, you can see that its propagators are dual to curves that go from a boundary to a boundary of the surface and cut through the propagators of the graph. Now, multiple collection of non-intersecting curves are dual to exactly one diagram. So the basic point is not to focus on the diagram, but on the curves. The advantage of doing so, the obvious advantage, is that there are many more graphs than there are curves. So it's easier to work with curves instead of graphs. Okay, so the first thing we do with curves is to associate them some kinematical quantities, something that depends on external momenta. The way to do that is to begin by representing the surface, choosing one, any way you want, one of the fat graphs that are dual to the surface, and assigning momenta to the graph in the usual way you do. So you assign momenta to the external legs, and then by solving momentum conservation to all the internal propagator. Now, every curve on the surface can be represented as a path that works through the fat graph. As it works through the fat graph, you can turn left, you can turn right, you can cross one of the rows of the fat graph. And we associate a momentum to the curve by, well, first we start with the momentum from the external leg from which we start. And then every time we turn right, so for instance, here the curve turns right when it enters the vertex, we add the momentum that enters from the left. So this is a simple rule that associates a momentum to every curve. Here I was doing a 3-level example, but if you consider a loop level surface, the momentum will in general depend on the loop momenta. An interesting fact about this rule is that recall that this is a single graph that we've chosen to begin at the start of the calculation, but we're associating momenta to all the curves, and in particular to all the graphs that are dual to those curves. So this is a way to sort of define a global momentum routing for all the graphs that contribute to that particular amplitude. And yes, we can also associate a propagator by taking the usual rule. Okay, that was the easy part. The non-trivial part is that we can also associate a certain function to this curve that we call a headlight function. To do that, first we associate 2x2 matrices to the elementary operation that the curve can do. So we said that the curve can turn left, can turn right, or can cross an edge of the fat graph. There is a matrix corresponding to turning to the left, a matrix corresponding to turning to the right, and a matrix corresponding to cross an edge that we label with some positive variable ye. Taking the product of all these matrices in the same order that they appear in the curve, we produce a new 2x2 matrix. And from this matrix, we compute a quantity that we call a u variable. So these u variables, so it's just looks a little bit like a determinant. So A times D divided B over C. These are sort of the heart of surfaceology. So everything comes from everything follows from properties of these u variables. Today we will consider a simpler version of the u variables. We will tropicalize them. Tropicalize means essentially that wherever we see in the expression for u a plus, we replace it with a max, a times with a plus, and a ratio with a minus. Importantly, there is no rule to replace minus with everything, with anything, but it doesn't matter because you see there are no minus signs in the matrices, so you will not find minus signs in the final expression. Okay, with these two simple rules, a rule for the kinematics and a rule for the headlight function, we can compute amplitudes. We represent them, as I said, as a single integral, and we can start looking at the integram to begin with. Is an exponential of something that looks like an action, is a sum over all the curves that you can draw on the surface. Each curve contributes with its propagator, built out of the momentum, times the headlight variable, the headlight function. Then if the surface is a loop level surface, you integrate over the loop momenta. And finally, you integrate over, well, recall that there was a matrix that depended on these positive variables that we associated to the road of the fat graph. We take the logarithm of that variable, we call it t, and we integrate over the possible values of t. Y is positive, so t is from minus infinity to plus infinity. Finally, we have to do something. We have to mod by a certain symmetry that acts on this integrand. But today will not play a particular role, so we can safely ignore it. Okay, the claim is that this integral is the scattering amplitude. So here are some examples. Maybe you recognize the handwriting is not mine. This is a 3-level amplitude. This is a 1-loop level amplitude. Here there is no loop integration. We will see in a second how to deal with that. But you know, if you want, you can just type these into Mathematica and integrate, and you will find the result for the 3-level amplitude in trace of AQT. So how does it work? Okay, I do not intend to go into the detail, nor giving any proof, but I just want to explain you mechanically what is that makes that formula work. The crucial point is to think about the headlight functions, how they look like. So if you recall, we obtained them by producing producing maxes by replacing max plus with maxes, so they are piecewise linear functions. What we have to do is to look at the domains of linearity, more precisely at the common domains of linearity of all these headlight functions. I claim that these are in one-to-one correspondence with the possible diagrams that you can draw on the surface. So if you were to plot them and look at them, you will find a picture like this, where the entire space is divided into cones, and each cone can be uniquely labeled by a Feynman diagram. The curve integrand in a particular cone collapses to the Feynman parameterization of that particular diagram. So if you integrate everywhere this integrand, and you break the domain of integration into Feynman integrals, you simply recover the usual formula for an amplitude, a sum over the Feynman diagrams. However, you do not have to necessarily decompose the domain of integration into Feynman integrals. You can decompose it any way you want. And this is going to play an important role in the numerical strategy. Okay, to connect with this idea of tropical sampling, we have to formulate the integral as a parametric integral. So we have to get rid of the loop integration. This can be done in a standard way that was just reviewed for us by Stephen. So we simply perform the Gaussian integral. That means that we have to take the Gaussian, the argument of the exponential, and separate it into the quadratic part, the linear part, and the constant part with respect to the loop momenta. And out of this separation, we produce simple polynomials that play the role of the Szymanski polynomial that we just saw in the previous talk. Then again, by the Chang-Wu theorem, really what you do is that you can rescale all the headlight function by a common scale and integrate it away. And so you can rephrase the Gaussian integral as a projective integral that depends on these Szymanski polynomials, and as an overall gamma function, whose argument is what is usually called the superficial degree of divergence. That's the number of edges of your graph minus loop number times the alps, the space-time dimension. Something a little bit unusual is that, as we just saw in this curve integral, this curve integral receives contribution from various graphs, and not all of those graphs are precisely loop-level graphs, in the sense that some of them could have propagators that carry three-level momenta. So think of something like a three-level structure added on the graph. And typically, we do not include that propagators in the counting of the superficial degree of divergence. We include only the connected part of the graph. But in this formula, I decided to do like that. So I pull out a common gamma function to all of this. Okay, so that was the curve integral. That's the object we want to evaluate numerically. So let's see how to do it with this idea of tropical sampling. Okay, let me remind you how a Monte Carlo integration looks like. So say that you want to compute some integral of some integrand I. The first thing I'm going to do is to divide and multiply by some other distribution j. And I'm just asking this j to be an honest probability distribution, something normalized to 1, but you can choose it any way you want. So what you want to do is to generate sample distributed according to this distribution, and use as estimator for your true value of the integral the average of the new integrand I over j on the sample points. Of course, as the number of samples goes to infinity, these estimator converge in a statistical sense to the true value of the integral. But what is most important is how fast it does that, so how precise this estimator is. The way to quantify how precise it is to compute the variance of this random variable. And a simple calculation shows that it is equal to 1 over n, the number of samples, times the variance of the integrand with respect to the other distribution that you chose, j. So the way to make this number small, so to make the estimator precise, is, well, of course, either increase the number of samples or choose wisely the distribution j so that the numerator becomes small. This technique is called importance sampling, and it's a very general problem, so there are very general solutions to it. Mathematica will do it automatically for you. But the question is how to do it in a smart way, in some way that knows about the structure of the problem. So the basic insight of Borinsky was to use as a sampling distribution the tropicalization of the original integrand. Here, the tropicalization is something slightly different, equivalent, but slightly different to the tropicalization I introduced before. Here, we simply replace plus with max, but we don't do anything else. In other words, these are polynomials, and this is just saying that we replace this polynomial with others that in every point of the integration space are simply equal to the leading monomial of your polynomial. So the tropical integrand is sort of an approximation to the original integrand. And this is the sense in which you expect it to look like the original integrand, and therefore to give you a small variance. This is the intuition. Okay, so the goal now is just to generate sample distributed according to this tropical integrand. So we have to do two things. First, we have to normalize this tropical integrand in such a way that we get an actual distribution. So we have to compute the curve integral associated to that tropical integrand. Now here we're thinking about curve integrals. If this was an ordinary integral, this quantity would be called the hat bound, something that was introduced by Eric Panzer for slightly different reasons. And then we have to understand, once we normalize it, how to generate efficiently sample points distributed according to J. It has to be efficient because you have to generate lots of them to get a good precision for the estimator. The way to do that is using something called sector decomposition. Basically, we focus on the tropical integrand, we restrict it on certain domains, and we think carefully about how it looks like just in that domain. So we'll define a sector to be a collection of curves, non-intersecting with each other, but an ordered collection of curves. So if it was just a collection of curves, it would be dual to a diagram. And now I distinguish depending on the order. To this combinatorial object, we associate an actual place, an actual sector in the curve integral, corresponding to the region where the headlight variables, the headlight functions are ordered in the same way. So the first one is greater than the second one, and so on. Now, this sector can be easily parameterized, reparameterized as a cube by doing these simple monomial changes of variable. We assume that t is to be between 0 and 1, so evidently this makes so that alpha 1 is greater than alpha 2, that is greater than alpha 3, and so on. It just so happens that in this region, the tropical integrand collapses to a simple single monomial. In the new variable, it will look like t raised to the superficial degree of divergence of the surface that you obtain cutting along the curves in the order in which they appear. Okay, this is a monomial, so modulo changing variables, going to the logarithmic variables and perhaps rescaling the logarithm. This is essentially a uniform distribution. So in this sector, we know how to sample from the tropical integrand. The last thing to do is to sample among the sectors. But this is also easily done because the integral of this function from 0 to 1 is just equal to 1 over the product of this superficial degree of divergence. So the entire hat bound, the normalization factor, is just the sum over all sectors of this single contribution. And what we have to do is simply to sample over the sectors. And once you have sampled a sector, you sample a point in it by going to the logarithmic coordinate and sampling uniformly. The problem is that there are just too many sectors. So even just enumerating, you could imagine of creating a list in Mathematica and then picking them according to a probability. But even just enumerating them, it's impossible. Because how many sectors we have? Well, first, you see, I was saying that we consider a collection, an ordered collection of curves, but just the collection of curves gives you a graph. And for every graph, of which you already have many, you also have to consider all the permutation. So this number is just impossible to deal with. Now, Michael Borinsky's approach gets rid of the factorial, but does nothing to deal with the growth of the number of graphs. So also that method doesn't really help us. So to solve this problem, we have to use this idea of decomposing the curve integral in a way that has nothing to do with Feynman integrals, with Feynman diagrams. So we define really what we do is the dual barycentric decomposition of the original decomposition. So it has to do with it, but the cells of this decomposition are really overlapping with the original ones. So we define a cell alpha DC requiring the corresponding, so for every curve there is a cell DC. We ask the corresponding Henle function to be the maximal one, to be greater than all the others. And so if this is maybe a section of our original decomposition of the curve space into Feynman diagrams, the black triangles could correspond to Feynman diagrams. And these cells are these dual barycentric regions. So you see they receive a bit of contribution from many diagrams. In particular, this is also a way to mod by the mapping graph group. But really what I wanted to show you here is again that one of these cells, sorry, in this picture, the sort of cones delimited by the rays are in correspondence with Feynman diagrams. But a region where you have to iterate receive a contribution a little bit from one diagram and a little bit from another one. Now, I will not show how, but a simple manipulation shows that the integral over one such a cell produces a recursive formula for the head bound, for the normalization factor. You have to sum over all possible curves up to this mapping graph group that I didn't really talk about. And each such cell contributes with 1 over the superficial degree of divergence of the surface that you obtain cutting along the curve times the entire head bound of that surface. So we find this new formula. Now, from this formula, we produce a new way to sample. Basically, every curve contributes to the total head bound. So you, instead of picking directly a diagram or directly a sector, you pick one curve after the other. You pick a curve with a probability that is that is equal to its contribution to the total normalization, so to this number. So the idea is that you start from a surface, you pick randomly a curve on it according to that probability, you cut along that curve, you produce a new surface, and then you continue until you have nothing left to cut because you degenerated the surface to a collection of triangles glued together by their sides. So this is a diagram, a Feynman diagram. But the order in which you have cut the curve gives you a particular sector of that diagram. Okay, this is just formulated not in words, but in a certain algorithm, but it's the same algorithm. And these are some tests, some results. So here I've computed, I've used this algorithm to compute numerically amplitudes associated to surfaces. So these are sort of tadpole surfaces with one external leg, so not exciting, but of increasing genus that corresponds in an increasing loop order. So we go from 2 loop order down to 10 loop orders. This is the number of graphs that contribute, of thought graphs that contribute. So we go from 1 to 120 billion. But the most important number is this column. This is the number of samples that are necessary to achieve a target precision. Here I was doing a 1-digit precision, really, to see how they scale. The important thing is that this number doesn't grow as much as the number of graphs would suggest. Because if you try to evaluate just a few of the diagrams contributing to the amplitude with the standard method, the Feintraub algorithm introduced by Michael Borinsky, you will see that the number of sample points required to achieve that precision is roughly the same, the same that you require for the entire amplitude. So this dual way of sampling is buying us a lot. Instead of having to generate all these diagrams and this number of samples per diagrams, more or less we need just that number for the entire amplitude. So this is a strange phenomenon. I don't know really how to explain it, but the way I think about it is as if you had it looks like the curve interend is some very smooth distribution, and we're breaking it up in lots and lots of pieces. But in doing so, we lose some information. So we lose the fact that the interend is actually much smoother, and to evaluate it, we don't need so many points. Okay. So this was the result for this very restricted setting. I just wanted to explain real quickly how the idea can be extended. Yes, so to go beyond trace of a cube in D equal 2, what we need for a general theory is a parametric curve interend. I should have mentioned that in surfaceology, there has been over the last year, lots of progress in various directions from many people in the audience, like Anastasia and well, many others. I don't see anyone else right now. And that extended the theory to other theories. But what we need is to formulate the extension for another theory as a parametric curve integrand rather than a loop curve integrand. And the important question is, how do we decide whether a parametric curve integrand is better than another one? And because we want to do numerical integration, we need to sample the integrand on many points. The most important thing is to find a fast numerical integrand, something that you can numerically evaluate fastly. And this is actually something that we used implicitly already here. I didn't comment too much about it, but one of the polynomials, for instance, is the determinant of a matrix. And knowing that this is a polynomial, like a semantic polynomial, doesn't really help us to evaluate at that point. But a determinant is something that we can evaluate very quickly. So we need this kind of phenomena. For instance, suppose that we want to deal with UV and infrared divergences. Something that I didn't say is that surfaceology is naturally formulated in dim reg because these integers have epsilons all over the places. So we could imagine of expanding the amplitude in epsilon, Laurent expansion in epsilon. And the question is whether we can find an efficient curve integrand for each order of the expansion. Now, we want to numerically evaluate it, so we really have to find an integrand, not just an integral. So we could try to apply this type of local subtraction formula that existed to compute these orders. For instance, an important one is the zero momentum subtraction in parametric space as formulated by Francis Brown and Dirk Reimer. However, this type of formula involves a sum over all the forests that belong to a graph. So there are secretly exponentially many terms in this integrand. So this is not a very good integrand to evaluate numerically. A better solution is to use sector decomposition again, since eventually we sample a point in every sector. And an interesting fact about sector decomposition is that this subtraction formula in a given sector factorizes, and so it's much faster to evaluate. If you want to go, this was about the divergences. If you want to go beyond the trace by cube, well, we have to understand how to do colorless theories. I spoke about it at QCD Meets Gravity 2024, so you can look at the talk. And beyond colorless theories, the next question is how to deal with spinning particles. Again, spinning particles means that we have a numerator in loop momentum space. We can convert it in a parametric one. Here, the question is how to, just by applying Bick's theorem to the Gaussian integration, the question is how to numerically evaluate it fastly. So put it simply, how would you count very quickly big contractions from the Gaussian integration? I don't know how to do this. I think a good idea is a derivative trick that was described in a book by Sebastian Miser and Offi Amesdottir. And okay, I'm done. So, questions?